Hello everyone, my name is Caleb Frillick, and today I'll be presenting on image denoising using wavelet transform techniques. In this presentation, I'll briefly introduce the problem of noise in imaging, discuss traditional and modern denoising approaches, and show how wavelet transforms provide a powerful method for restoring images. I'll also walk you through a MATLAB-based demonstration comparing results from different techniques. Let's begin. Image noise is a common and critical issue in almost every imaging system, whether it's photography, medical imaging, or satellite imagery. Noise can come from a variety of sources, from low light conditions to sensor errors, and it can seriously degrade image quality by hiding important details. That's why image denoising is such a fundamental task, improving visual quality and making it easier for both humans and machines to interpret the image correctly. But not all noise types and methods are created equal, and that's what we'll start by exploring next. There are two main types of noise models. Additive noise adds a random signal to the image, while multiplicative noise scales pixel values. Recognizing these helps tailor our denoising strategy. When it comes to specific types of noise, Gaussian is the most commonly assumed. It's random, it's normally distributed, and it leads to grainy or snowy images. If we were to plot the amount of distortion of a pixel value against the frequency with which it occurs, you would expect to see a normal distribution, hence the Gaussian name. While other noise distributions are possible, the Gaussian distribution is typically a good model due to the central limit theorem that says that the sum of different noises tends to approach a Gaussian distribution. Speckled noise is most often seen in radar and ultrasound images. It's more complex because it multiplies the pixel values rather than just adding a random variation. In salt and pepper noise, pixels in the image are very different in color or intensity from the surrounding pixels. The defining characteristic is that the value of a noisy pixel bears no relation to the color of those that surround it. When viewed, the image contains dark and white dots, hence the term salt and pepper noise. Generally, this type of noise will only affect a small number of image pixels. Typical sources include flecks of dust inside the image camera, and overheated or faulty CCD elements. There are other types of image noise, including periodic noise, which shows as patterns due to electrical interference, shot noise, a result of quantum fluctuations in photon detection, and uniform noise, among others. Identifying the type of noise is important because it influences which denoising method will work best. Denoising methods fall into two main domains: the spatial domain and the transform domain. While spatial method filters directly on pixels, transform methods, like wavelets, work in the frequency domain and can preserve more detail. In the class we took a look at mean and median denoising methods, and in my project I focus exclusively on understanding some of the capabilities for image denoising in the transform domain. The wavelet domain offers several powerful denoising techniques, and we won't have time to discuss all of these methods, so we'll focus on the left side of the chart, looking at linear filtering and nonlinear threshold filtering in the wavelet domain, and we'll discuss what this means in a few slides. In order to understand how we can use wavelets for image denoising, we first must understand what wavelets even are. From a high level, a wavelet is a small oscillating function with zero mean and finite energy. These properties make wavelets ideal for analyzing signals with localized features in both time and frequency. The term wavelet comes from a French word meaning little wave, and considering some example wavelets on the bottom of the slide, we can possibly see where the connection to the ocean stems from. One important thing to remember is that wavelets are families of functions that can be modified by key parameters that define the wavelet. All wavelets have, at minimum, two parameters: a scale parameter and a position parameter that controls the stretching or compression of the wavelet and the position of the wavelet in time or space. As an example, we show the scale and position parameters for the Morlet wavelet, a typical wavelet used for signal analysis. As we mentioned, wavelets are special functions that can analyze a signal at multiple scales or resolutions. They're essentially like zoom lenses for data. Unlike Fourier transforms, which only give us frequency information, wavelet transforms provide both frequency and spatial or temporal information. In the example, we illustrate this by computing the wavelet scalegram, showing the presence of each sine frequency across time. The ability to see in both frequency and that spatial or temporal domain makes wavelets especially powerful for image denoising because they can separate important features, like edges, from random noise as a function of pixel location. This slide illustrates at a high level how the wavelet transform works mathematically. Wavelets of different scales are formed and translated across the signal. The product of the signals is integrated and forms a data point in the continuous waveform transform domain. In the discrete waveform transform, we obtain coefficients as a function of scale and translation. Increasing the scale stretches the wavelet and reduces the number of coefficients across the translation axis. In images in 2D wavelet transforms, we use two wavelets, a father wavelet for capturing smooth, low-frequency trends, and a mother wavelet for sharp, high-frequency changes. Together, they allow us to decompose the image into meaningful subbands. The image on the right depicts the mother and the father wavelets for the dB2 wavelet. Father and mother wavelets are used to transform the image into subbands. Each subband captures directional features. If we low-pass filter the rows and the columns, we obtain an approximation of the smooth, low-frequency content of our image. If we low-pass filter the rows and high-pass filter the columns, we obtain vertical edges. And inverting that, we obtain the horizontal edges. If we high-pass both the rows and the columns, we obtain the diagonal textures and corners. The figures on the right show the single level of wavelet decomposition into subbands using the dB2 wavelet. There is no noise in this original image, thus we see that the detail that the wavelets capture in detecting edges along each dimension. In wavelet image denoising, we can chain together subband decompositions of the original image. Each time we do so, we downsample the coefficients by a factor of 2. Multi-level decomposition enables more targeted and effective denoising by further separating noise and signal features across spatial frequencies. Lower levels, level 1, capture fine details and high-frequency noise like sharp edges or grainy patterns. Higher levels, like levels 2 or 3, capture coarser features and broader patterns, including low-frequency noise. After decomposition, we apply filtering to the detailed coefficients. The detailed coefficients contain edges and fine textures at each scale, but they are also the bands where noise is most prominent. Applying thresholding or Wiener filtering here effectively removes small high-frequency noise while preserving larger, meaningful features. Wiener filtering is a linear filter that minimizes the mean squared error between the desired signal and the filter's output, and is effective against Gaussian noise. Nonlinear thresholding does not rely on a global noise model, making it more robust with different noise types. There are two main types of thresholding, hard and soft thresholding. Soft thresholding generally reduces smaller coefficients, whereas hard thresholding zeroes them out completely. The process of denoising with wavelets can be thought of as having 3 stages. First, decompose the image with the discrete wavelet transform, then threshold the detailed coefficients, and finally reconstruct the image using the inverse transform. There are hundreds of algorithms, maybe not quite that many, but there are a lot of methods that inform how to set the threshold levels. Some of the most common and also implemented in MATLAB are methods like Visu shrink, also known as the universal threshold, Bayes shrink, and Schur shrink, that all work in the same vein, estimating some noise statistic or error term from the image or coefficients, and then designing a static threshold to apply. To evaluate the success of denoising, metrics like mean squared error and peak signal-to-noise ratio are used for error measurement. Structural similarity index is used to quantify perceptual quality, and visual inspection of the images themselves is used to assess structural preservation. We'll take a look at some of these metrics in our MATLAB analysis. Our MATLAB implementation setup consisted of a library of standard images with various noise types applied and traditional and wavelet methods to denoise those noisy images, And then we also compared error metrics like MSE, PSNR, and SNR. We don't have time today to exhaustively explore the space analyzed, so I'll show you a couple of high-level results for the Lena test image. Here's an overview of our denoising results across noise types and denoising methods for the Lena test image. In this example, we're using rather limited noise. Gaussian noise with a standard deviation of 5% of max pixel intensity, and the same percentage for the variance of the speckle noise. The noise assumptions for the other sources are shown in the table. We're using the dB2 wavelets with the 2-level decomposition. Interestingly, we don't really see a huge performance gain with the wavelet methods. For Gaussian noise, wavelet methods performed comparable to traditional filters. Wavelets excelled for filtering out shot noise because it isolates high-frequency components where the noise is most prominent, allowing subtle signal-dependent variations to be suppressed without blurring. But traditional filters, like median filtering, performed better for impulse and speckle noise. Before you think that wavelets have little utility, consider the effect of using traditional methods as the noise floor is varied. Using the same Lena image with Gaussian noise, we vary the noise standard deviation from 5% of max intensity to 25%. In the images on the right, we note that as the noise standard deviation increases, eventually the traditional methods become susceptible to increased noise floor, while wavelet-based thresholding denoising methods are able to adapt across multiple scales and suppress noise without over-smoothing important features. It is interesting to note that past a noise standard deviation of 15%, the three wavelet methods collapse on top of each other, which indicates that thresholding has little effect at this noise level for this image. It's also fascinating that extremely low noise levels, wavelets do a much better job of capturing the small variations in the image. In the intermediate range, kind of from 5% to 15%, wavelets, the results are fairly comparable within a few dB. Another knob that we can turn in our wavelet denoising toolbox is the number of decomposition levels that we apply. Here we fix the noise and change the number of levels for the dB2 wavelet from 1 to 5. Interestingly, universal thresholding degrades with increasing wavelet levels because it applies a fixed global threshold that becomes overly aggressive at finer scales, leading to loss of important signal details. Schur and Bayes shrink methods improve with more levels up to level 3 where they stabilize, and this reflects their ability to adaptively threshold detailed coefficients, but it also shows diminishing returns beyond a certain scale depth. So where can we go from here? What other wavelet-based approaches could improve denoising? And if you harken back to the hierarchical classification diagram from before, you'll remember that there are entire branches of the wavelet denoising domain tree that we didn't even explore. I took a brief look on the internet at some research articles that described complicated methods and algorithms that utilize wavelets for image denoising. Some of the ones that I was able to understand involved using adaptive thresholds through methods that MATLAB already has employed to capture variation in noise level across subbands, or using non-orthogonal wavelets to prevent edge artifacts after taking the 2D wavelet transform. There's also some cool looking work taking a look at context-aware filtering that is spatially adaptive as well as subband adaptive. To wrap up, we explored how different types of image noise impact image quality in unique ways. Wavelet-based denoising is especially powerful because it works across multiple scales and directions, allowing us to remove noise while preserving key image features like edges and textures. Thresholding techniques proved effective, especially at high noise levels and for signal-dependent noise like shot noise. We also saw that for impulse and speckle noise, traditional methods like median filtering still performed well. Choosing the right wavelet level and method is crucial, and going forward, using adaptive thresholds, non-orthogonal wavelets, and spatial context models, among other attempts and approaches, can further improve denoising performance. The field of wavelet analysis is broad and complex, and I encourage you to dive deep and learn more. Here are the sources that I utilized. I would highly recommend the video by Artem Kirsanov entitled Wavelets, Mathematical Microscope. It was a great introduction to the topic for me. Thanks for paying attention. If you have any questions, feel free to reach out to me via email.